So, yes, this is going to be the first of a couple of lectures on error correction, quantum error correction. I come from classical error correction, and I tend to adopt the viewpoint that you really want to look at quantum error correction from the point of view of classical coding. You don't have to, but classical coding does shed a lot of light on quantum coding. Quantum coding borrows a lot from classical coding. So I would like to start with a couple of notions from the basics of classical coding, and then we will see how all this gets transposed into the classical setting. So, classical codes. So how do they work? What is classical code? You can think of it as a subset of binary vectors. So subset of f2 to the n. That is an f2 vector space. So it's stable by addition. So what is the simplest way of thinking about classical code? How do you encode? You use what is called a generator matrix. So 0, 1 matrix with rows G1, G2 through to GK, and you encode like this. You take k tuples of information from f2 to the k, and you embed them in f2 to the n. So rows of the generator matrix have length n, and encoding simply goes like this. You take a k tuple, multiply by g. In other words, add the rows m1, g1 through to mk, gk. So the mi's, they're just bit the zeros or ones, and these are n tuples. That's it. So you transform k tuples of information into n tuples. So the simplest possible example of an error correcting code is you start from f2, you go to f2 to the 3, and you change bit m into m times the triple 111. So, in other words, you're just repeating m 3 times. So coding doesn't get simpler than this. And then, what is all this for? It's to solve the decoding problem. So what is the decoding problem? Errors occur. So you start with a code word C, and then this code C gets tortured in all sorts of ways. Noise gets added to it. So you're given as input a code word which is corrupted by a vector E, and the vector E, the error vector, you think of it as an error of small weight. So it's a binary vector, and it means it doesn't have too many ones. So you're given this y, and you want to decompose this sum. Find the original code word, equivalently find the error vector E. So For the repetition code, it's kind of very easy. For example, you receive this, and you have to find the closest code word, the smallest error vector that will get you to a code word. Well, there are only two possible choices, and you see that the best choice is to consider the all one vector. You only need to change one bit to get to a code word, the all one vector. If you try to get to the all zero vector, you need to change 2 bits. So this is the solution to the decoding problem. Okay, there's an alternative way of thinking about a linear code, which is you don't think about a basis of the code. You will consider what coding theory jargon names parity check matrix for the code. So when you learn linear algebra, you learn that vector spaces can be described in 2 ways. You can give a basis, or you can give a set of equations. So a vector space alternatively gets described as a set of equations. So parity check matrix is a set of vectors who give you the coefficients of an equation, h1 through hr, again, n columns. And the really most important object of coding theory is the syndrome function. So what does the syndrome function do? It goes from f2 to the n to f2 to the r. And what does it do? It takes an n tuple of bits of zeros and ones, x1 through to xn, to a column vector, which is inner product of the first row here, h1 and x. X is the vector. So if you prefer, explicitly, this is x1 multiplied by h11 all the way to xn multiplied by h1n. And similarly, for the other coordinate, the ith coordinate of the syndrome is the inner product between x and row hi of h. I've written the parity check matrix as a set of rows, but you really want to think about it as a set of columns. h1 through hn. And written like this, what does the syndrome function do? Syndrome of x is x1 times column h1 plus xn times the nth column, column hn. And the code is the set of binary vectors with 0 syndrome. This is a column vector. So in the very simple repetition code example, you can introduce this little matrix. And you can see that the set of vectors which have zero syndrome is just the all zero vector, which is always there, and the all one vector. So these equations represent the repetition code, and the syndrome function is especially interesting for decoding. So once again, it's kind of a trivial example, but nevertheless. Say you receive y, what could you do? You can compute the syndrome of y. Now the syndrome is a linear function. So if y is a code word plus an error vector, this is always going to be syndrome of c plus syndrome of the error vector e. And syndrome of c, if c is a code word, by definition is 0. So you compute the syndrome of the received vector, it's always going to be equal to the syndrome of the error. And then to decode, all you have to do is figure out what is E from syndrome of E. So in our example, computing syndrome of E, it just means adding the first and second rows of the parity check matrix, which gives you the vector 1, 1. And here you realize that this is the syndrome of 0, 0, 1. This is column H3, in other words. So if it's column H3, you get that the error is in position 3. All this may look a little trivial in the case of the repetition code, which is trivial to decode anyway. But this idea is extremely powerful, and it enables you to define define much more powerful code. So for example, slightly more complicated than the repetition code. So notice here, the repetition code, it has a parity check matrix which consists of all distinct binary columns of length 2. So we could take all distinct binary columns of length 3 and see what happens. For example, and you could apply the same decoding procedure. So for example, suppose you receive this vector. So what you do, compute the syndrome of y, and what does it mean? It means you need to sum all the columns that corresponds to positions where there's a y, where there's a 1 in the vector y. That's it. So you add them together and you see that you get 0, 1, 0, and you look at the matrix for the moment and you realize that this is H2. So what this means is that to get a code word, all you need to do is change position 2. There's an error in this position, or in other words, you will get a code word if you change the second bit to get this. So more generally, to decode, what you want to do, you want to compute the syndrome of the received vector and write it as a sum of columns of H that involves the smallest number of columns possible. So sum for I belonging to some set of coordinates I of minimum size. And that will solve the decoding problem for you. An important quantity, minimum distance, this is the smallest weight vector C of zero syndrome. So if you prefer, vectors of zero syndrome are code words, so it's the smallest weight of a zero code word. And a remark which is very useful is that in theory we can always correct an error vector E of weight strictly less than half the minimum distance of the code. So why, you can see it on an example. Suppose you have minimum distance 5, you want to correct 2 errors. What does it mean? It means you want to write the syndrome of your error as a sum of 2 columns. Now, suppose there were 2 ways to do this. Suppose this could all be written as HA prime plus HJ prime, for example. Then put all this on the left. Thank you. Okay, maybe this isn't the best permutation. Never mind. So, continuing from the top, if you had this, it would mean that HI plus HJ plus HI prime plus HJ prime would be equal to 0, but then this means that you have a code word of weight 4 with 0 syndrome. but that's not possible if we suppose that the minimum distance is 5, and this argument easily generalizes to any minimum distance. So this is the essence of coding theory, classical coding theory. The parameters of a classical code, they give you a vague idea of how good a code is, but they don't tell the whole story. It's only 3 numbers. So this is the length, n. It means you're in the ambient space f2 to the n. You're dealing with n tuples. This is the dimension. It gives you the number of code words. It tells you that your number of code words is 2 to the k. All the ways of creating your code words, if you want, from a generator matrix with k rows. And this is the minimum distance. Sometimes I'll just say the distance that we've just introduced, and that gives you a lot of information on how many errors you can correct if you can solve the decoding problem. So, another couple of words on the decoding problem. In theory, we want to do this. We're given some vector y, we compute the syndrome, and we want to write the syndrome, this column vector, as a sum of the smallest possible number of columns of the parity check matrix. Right. In our little examples, it was just correcting one error, writing the syndrome as just a single column of the parity check matrix. If you want to correct 10 errors, you realize you're going to have an algorithmic problem. What do you do? If you do brute force exhaustive search, you're going to look for all possible n choose 10 ways of choosing a vector of weight 10. And if n is, I don't know, 100, this is already not feasible. There's some generic ways of improving this, but they don't get you very far. The decoding problem, unfortunately, is NP complete. So it's unfortunate for people who want to correct errors. It's fortunate for people who do cryptography, in particular post-quantum cryptography, because you can recycle this to construct interesting crypto systems. That's another story, and I won't be telling it. But this is a real issue. So you need to devise codes that will actually come with an efficient decoding algorithm. So there are many ways of doing this. You have algebraic coding theory, which uses a lot of algebra to construct good codes. And I'll just say a couple of words on the theory of low density parity check codes. So simply called LDPC codes. That were introduced a very long time ago. So the idea is very simple. You just choose the parity check matrix H with not many ones. That's basic idea. So choose your columns and your rows with some constant weight and a large block length n, which will make the density of the parity check matrix, the ratio of the number of ones over the number of coordinates, very small, hence the name. So why is this an interesting idea? Well, because you can imagine that this is going to help decoding, right? So when you compute the syndrome, you're computing equations. So code word should satisfy equations, and if they're of small weight, your equations will look like this. If you have a row of weight 3, for example, you'll have an equation which will look like x3 plus x7 plus x35, for example. It should be equal to 0, but when you compute it, you may get a 1. And if you get a 1, what does it mean? It means that you have at least one error in positions 3, 7, or 35. So you haven't exactly localized an error, but you've done nothing, and already you know that there's an error either in position 3, 7, or 35, and that's already a lot of information. And maybe you will get another equation that tells you x3 plus, I don't know, x11 plus x27 is also equal to 1. And then you will think, oh, it's really extremely likely that I have an error in position 3. If I just change the value of bit number 3, those two equations all of a sudden will be corrected. I'm not going to say any more about generic LDPC decoding, but that's the basic idea of why LDPC codes are interesting and why they tend to come with efficient decoding algorithms that will do variants of this. Actually, this idea needs to be a bit more organized. I'm not going to go into it so much, but thousands of papers, and I mean this literally, have been written on exactly this subject and what is the right way of decoding LDPC codes. Yes?
And so does it mean that the problem becomes not NP complete when you have a low density parity check?
No, it doesn't. Yes, so does it mean that decoding is not NP complete anymore for the subclass of LDPC codes, right? So, no, it doesn't really mean this. The decoding algorithms for LDPC codes, they don't do complete decoding. They don't really solve the complete decoding problem, or they're not able to find all solutions to the decoding problem, but they will work very well in cases where the weight of the error is not too large. It's smaller than you would want to correct if you wanted to solve the complete decoding problem. Okay. Okay. Probably I want to do this. So LDPC decoding is typically suboptimal, but it does a great job of correcting typical errors, not worst case errors, which you would want if you want to go from NP complete to polynomial. But this brings me to a particular subclass of LDPC codes, and these will be my last words on classical coding. And this subclass is really very relevant to quantum coding, as I hope to show you soon, maybe not today, but if not today, then next time, where I will try to talk to you about quantum LDPC codes. So there's a subclass of LDPC codes which are kind of the simplest possible LDPC codes. You will ask for the number of ones per column to be exactly 2. So 2 ones per column. Choose matrices with exactly 2 ones per column. And if you do this, you may define a graph, and you may realize that your matrix H is nothing but the incidence matrix of a graph. You will call all the rows of the matrix vertices, and you realize that a row, what does it tell you? It tells you that there's an edge between 2 vertices. If you have ones in position A, B, you will draw an edge between A and B and define a graph. And now a row a row of H corresponds to some vertex, say call it A, and every one in this row, it gives you an edge in the graph. And now what is a code word? A code word is something with 0 syndrome. So it's a set, it corresponds to a set Z of 8 of a set of edges. So it's a 0, 1 vector, right? 0, 1 vector, you can think of it you can think of it support the set of positions where it is equal to 1, and these positions, we've just said that they're edges in the graph. So you can think of vectors in your ambient space now as sets of edges. And what is a code word? It's a set of edges with a property that for any vertex V, Z, V is incident to an even number of edges of Z. So you can draw little examples. For example, here is a graph. Here would be the rows of the matrix of a parity check matrix. And you may want to number your edges, so they correspond to coordinates. Maybe I'll use color here. 1, 2, 3, 4, 5, 6, 7, 8, for example. So here we've just created a code with of length 8 and a parity check matrix with 6 rows. And so, for example, row A will look like this. It will have a 1 in position 1, and also 2, 3, 4, 5 ones in position 6 and 7, because it represents this incident structure. So I'm not writing the whole of the parity check matrix, but you get the idea. And you see what is a vector which belongs to the code. What is a code word? It's a set of edges that meets every vertex in an even number of positions. Here there's no choice. It's going to be either 0 or 2 positions. And this means that code words are really cycles in your graph. So this family of code, this subclass, it's the class of cycle codes of graphs. So to get such a code, what you do, you choose your favorite graph, and all cycles in your graph will give you code words. So for example, you may take the most famous graph in graph theory, the Peterson graph. Which looks like this. And it gives you a pretty interesting code. Parameters, length is 15 because there are 15 edges. One may compute the dimension and figure out that it's equal to 6. So there's 64 cycles in this graph. You can count them. And the minimum distance, it's the minimum size of a cycle. So in graph theory, this is the girth of the graph, and you can see that the minimum cycle size is 5. So this code can correct 2 errors. And it's not the best possible code in length 15 and minimum distance 5. There's one with dimension 7 and not 6, but it's still pretty good. If you want to construct such a code by hand from scratch, it will take you time to figure out how to do it. Cycle codes of graphs in classical graph theory, they're some of the oldest codes around, and let me continue for half a minute and get back to you. They're not the best codes around by far. Typically, their minimum distance is not super good. Asymptotically, it doesn't grow very fast with a length n, but it has a huge number of very interesting properties. In particular, this time, decoding is polynomial time. Complete decoding is polynomial time, and to the best of my knowledge, I don't think there's any class of code that really eludes me. This is the only non-trivial class of classical codes for which we know of a polynomial time algorithm for doing complete decoding. in the context of quantum coding, this will be hugely interesting. Sorry, your question?
I think I have a fundamental question. I didn't understand why 7 would be better than 6. I thought we want to increase the dimension.
Well, you get more code words. Sorry, so the question is, why would a dimension 7 be better than a dimension 6? It's better if the other parameters don't change, because it means that you can encode messages of length 7, so your message size, it goes from 64 to 128 by using the same amount of resources. You're transmitting only code words, only vectors of length 15, and you can correct 2 errors because your minimum distance is fine. So for a long time, it was considered to be the fundamental problem of classical coding theory. Fix the length n, the size of your n tuples, the minimum distance you want to aim for, and find the largest possible code. Or conversely, given a dimension and a length, find the largest possible minimum distance for a code. This problem is still pretty much open. We have lower bounds, we have upper bounds, we have tables of the best codes for small lengths, but we don't know how to solve the general problem. It's not the only problem of coding theory. People don't necessarily think of it anymore as the #1 problem of coding theory, but it's pretty fundamental, yes. Okay. So this is pretty much what I wanted to say about, maybe this can go all the way. And damn. Yes?
How will this graph interpretation translate over other fields like F3?
Yes. So how are these codes called when we're not over the binary field, but when we're over F3, for example, other field sizes? So these codes are not super common and will not have a universal name, but if you have just a little background in homological algebra or topology, you will realize that these are still cycle codes. So they're the space of 1 cycles of your graph over F3. You can change the field size and you have still the notion of cycle. You can go to higher dimensions and have spaces of 2 cycles for larger simplicial complexes. So this terminology of cycle code and more generally cycle space is a pretty standard terminology in homological algebra, which goes beyond coding theory. So that's pretty much all I'm going to say about classical coding theory, at least for now. I might, if time permits, go back to it just a little to highlight some fine points of quantum coding theory. We'll see. So what you want to take away from this is the importance of the syndrome function. You might remember the example of our little code of length 7, which is called the length 7 Hamming code, and which in quantum coding translates into the Steen code that I will try and show you. And you may also want to remember the notion of the cycle codes of graphs that we will also encounter in the quantum context. So, quantum coding. So, the simplest classical code is the repetition code. So, the first thing you think of when you start from scratch and start to think about quantum coding is there an equivalent of the repetition code? And there you hit upon a somewhat serious issue. If you think about it naively, you would perhaps want to start from some quantum state and somehow repeat it like in the classical setting, but that's not allowed in quantum theory. The no cloning theorem tells you it's not possible, there's no unitary transformation that does this sort of thing. And for a short while, some people thought, okay, error correction is not possible in the quantum setting. We can't even do repetition. It rules everything out. But it turns out that, no, you can actually correct errors in the quantum setting. So you can do, to start with, you can do something which is a little more modest than this. So suppose you start from a quantum state which is just a single bit, so alpha 0 plus beta 1. What could you do? You can do the equivalent of classical repetition. How would it go? So you can start from this and add a couple of qubits, say in the 0 state, and then map this to this expression, 0 alpha times 0, 0, 0 plus beta times 1, 1, 1. So all you need to do to get this is to map 0, 0, 0 to 0, 0, 0 and 1, 0, 0, which you will get if psi is equal to 1, 0, 0. You want to map it to 1, 1, 1. But these two states are orthogonal, these two states are orthogonal. We know that there is a unitary mapping which does this. Actually, there are many unitary mappings which do this. We don't really care what it's going to do on the other basis states. And we will get this. We will transform our initial state here, and what we've done is some sort of repetition. We've repeated the zeros and we've repeated the ones. And what can you do with this code? Suppose we have this toy error model. Suppose we have X errors. So let me remind you that Pauli operator X, all it does is change the 0 basis state to 1 and the 1 state to 0. And suppose you wanted to correct the equivalent of classical errors. So you could envisage an X error, but just on the first qubit. So suppose you have this operator acting on our qubit, so just an X on the first qubit and nothing on the other qubits. And allow me to make this, to write this in a lighter form, so I don't write these tensor products all the time. I'll just write X identity identity. And now, suppose we're told that there's going to be an error, which is one of those three errors. Somewhat like in the classical case. So what does an X error do? It really just flips the first qubit. If it's on the first, if X is on the first qubit, or maybe it will act on the second qubit or the third qubit, and it will just be a bit flip. Okay, so in the classical setting, we could actually look at the state. We could had a received vector. Here, we have a quantum state. It's been corrupted. So instead of psi, we may get maybe alpha 1, 0, 0 plus beta 0, 1, 1. So we can't look at it in the eye and see that the first qubit has changed, but we can do some measurements. So we need to measure something. So what can we do? Let me reintroduce our little parity check matrix that we had before. Before, one way of applying error correction to the repetition code was to compute this little syndrome, the syndrome corresponding to this matrix. And basically, we're going to do the same thing. So how does it go? I will decompose the ambient Hilbert space, which is the basic Hilbert space of dimension 2 tensored 3 times, right? I can decompose it in this way. Let me write A 0, okay, 0, 0, plus orthogonal A1, 0, plus orthogonal A0, 1, plus orthogonal A1, 1. So what are these spaces? This is the space generated by the basis states of zero syndrome. So This is the space generated by 0, 0, 0 and 1, 1, 1. And this is the space generated by the basis states of syndrome 1, 0. So this is going to be generated by the basis state 1, 0, 0 and 0, 1, 1. And similarly, here I'm going to put the basis states 0, 1, 0 and 1, 0, 1. And here I will put 0, 0, 1 and 1, 1, 0. Okay? Obviously, these four spaces are orthogonal to each other, and we have this orthogonal direct sum decomposition. So we're allowed to do a measurement that will project onto these spaces. And you see that the original state, it actually belongs to 8, 0, 0 by construction. And if there's an X error on the first qubit, well, we will change the first coordinate here. We will fall into this state. If there's an X error on the second qubit, we fall into this state. If there's an X error on the third qubit, we fall into this last space. So when we do the measurement, we will find out that we necessarily fall into one of those four spaces. Starting from anything after the measurement, we will be in one of those four spaces. What happens if our error is of this X form, we will simply go from this space to one of those three spaces. So the measurement will tell us exactly which of those three errors occur. So our error vector here belongs to one of these AYJ necessarily. And when we do the measurement, we know which one it is. And if we believe that the initial error was of this form, then we will have the error E exactly, and we can apply it again. We can go from E times psi to E times E times psi. We apply E again because we found the error vector. And X squared is equal to identity, so E squared is equal to the identity. And we're back to the original state. So we still don't know what the original state is. We never do. We're never allowed to access the alpha and the betas. But we can go back into this state if we are promised that the only errors that can occur are of this sort. What have we done? We've really mimicked classical error correction. But this is not enough in the quantum setting. So suppose there's a Z error on the first qubit. Then we will get 0 alpha times 0, 0, 0 minus beta times 1, 1, 1. And now we're not in any of these states anymore. And this time we lost. I mean, if we do this measurement, we will destroy the state, and we're not going to get it back again. So if we told that we will either get an X error on one of the qubits or a Z error on one of the qubits, then we're going to lose. We're not going to be able to correct the error. We will have to make a hypothesis of the sort we either have an X-type error or a Z-type error. We will have to make a bet of some sort. Maybe I can stay like this. So, if we're going to correct quantum errors, we need to correct X errors and Z errors. That is going to be the challenge. Can we devise the quantum code that will correct, that will be able to correct either X errors or Z errors, or possibly even a mix of X and Z errors? Here you might protest and say, okay, suppose we managed to do this. Why would it be enough? I mean, why should we expect that errors will be of the type an X error on the first or the second or the third or the ith qubit, or a Z error on the first, second? The real world is likely to be much more messy than this. And you won't be right to raise this objection, but I will try and convince you soon that if we can deal with this problem of correcting pure X errors and pure Z errors, then we will be able to correct much more general errors. But let me postpone this to a little later. For the moment, bear with me. Let us try and look at this task of correcting just X errors and Z errors, which is already a challenge. Okay, let me start with a small remark with our little toy code here. The remark is, we kind of use this little syndrome matrix from classical coding. And let me transform it into a matrix of Pauli operators. So let me replace the 1s by z and 0s by identities. And let me make this remark. These two Pauli operators, maybe let me call them A and B, they stabilize our quantum state here. So if you apply A to alpha 0, 0 plus beta 1, 1, 1, then you see that every z operator really puts a minus here, but there are two z operators. So you're applying them twice. So the 1 is back to a plus again. So these two operators, they stabilize our quantum state psi. And that has something to do, it may help us to try and devise a measurable syndrome function. You see that what we did, we decomposed our Hilbert space into subspaces, a direct sum, an orthogonal direct sum of subspaces that corresponded to the values of this syndrome function. And it turns out that this has something to do with being stabilized by these two operators that are some sort of translation of our classical matrix here. Notice that these two operators, they only contain identities and z's. And this is something that enabled us to correct X errors. So what we might try to think is that if we want to correct Z errors, we might want to try and devise quantum states which are stabilized by Pauli operators that contain not only Z's but also X's. This may seem a little far-fetched, but it's the key to devising this large class of what are called stabilizer codes. So let me give the example of the 5-qubit code. People in courses on quantum error correction, one often presents intermediate one-error correcting codes, the Shor code, the Steen code, and then get to the 5-qubit code. I'll go immediately to the 5-qubit code, which is the smallest possible quantum code that corrects one error. What does it mean exactly to correct one error? We'll see as we define it. So let me do this. I'm going to define 4 Pauli operators. Which ones? These. So let me define M1 as X, Z, Z, X identity. Okay? These are really tensors. So this is the length 5 Pauli operator. What does it do? It applies an X on the first qubit, a Z on the second qubit, a Z on the third, an X on the fourth, and does nothing on the fifth. Okay? So they're really tensor products here, but I'm not writing the tensor products to make notation lighter. M2 is a cyclic shift of this pattern. So X, Z, Z, X identity. M3, I shift this cyclically again. So X, Y, identity, X, Z, Z. M4 is Z, X, identity, X, Z. That's it. There's a fifth cyclic shift, but this fifth cyclic shift is really the product of these four operators, so I'm not going to need it. These are a bunch of operators. Now, let me define the quantum code. So this quantum code, it's a set of states that is going to live in H tensor 5. So what does it look like? It encodes one qubit. So you start from some qubit in general position as before, like this. And using auxiliary qubits like before, I will transform this into alpha psi 0 plus beta psi 1. And what is psi 0? Psi 0 is defined like this. It's the sum over all operators little s in large S. I haven't said yet what large S is. We write M. So M applied to the 0 state. So now 5 qubits. And psi 1 is the same thing applied to the all one computational basis state. Okay, so what is S? S is it's a group of operators generated by the MI, M1, M2, M3, M4. So you may want to notice that S is abelian. These operators, they commute. So on one qubit, you may want to remember that X and Z, they anti-commute. X times Z is minus Z times X. And when you do this sort of thing simultaneously, you see that X commutes with identity. Also, here, Z commutes with itself, but Z anti-commutes with X, and X anti-commutes with Z. So both of them together, they cancel the minus, and you get that these operators, they actually commute. And you see that they all commute pairwise. If you take any two of them, you have two coordinates, and an even number of coordinates where you see Z and X or X and Z. Yes?
I get confused by the notations.
Yes?
The N1 is a tensor product or a dot product?
Yeah, this is a tensor product. So no, commutation is for composition of operators. Or means that if you start from some state phi and you apply the operator M1, so applying the operator M1, it means you apply x to the first qubit, z to the second qubit, and so on. And then to this new state, you apply the operator M2, you will always get the same result as applying first M2 and then M1 for any state phi. It's commutation for composition of operators.
The point is that the product of the right, upper right, is in fact a composition.
Upper right?
Upper right.
Here, yes, this is composition.
But it is not that just like the transform product. So this is why it may confuse.
Yeah, this is only on one qubit. So there are no tensor products anymore because it's just one qubit. So if you prefer X identity 4 times multiplied by Z identity 4 times, here you will have tensor products. This is a matter space. You will have commutation. This will be X1111 multiplied by Z111 on the left, okay? So we may define these states, and you can see that the MI operators, they all have 2 x's in them. So when you apply an MI operator to the all 0 state, you're going to flip 2 qubits somewhere. And the Z operators, after a time then, may add minus signs all over the place, never mind the minus signs. But all these states, they will have an even, the computational basis states that are involved, they will all be of even weight. And if you start here, they will all be of odd weight for the same reason. So this state may look pretty complicated if you write it out explicitly. It will be a mess of plus and minus ones between the even weight computational states, but here it will only involve odd weight, so we get that psi 0 is orthogonal to psi 1. So because psi 0 is orthogonal to psi 1, there's clearly a way of doing this transformation. And if you look at it a little more closely, you will see that this space of quantum states, so generated by psi 0 and psi 1, is exactly the space stabilized by S. So by construction, clearly, psi 0 is stabilized by any M in S. Psi 1 is also stabilized by any M in S. And there's nothing else, states which are stabilized by M and S, but are just these states. I'll get this one. let me now define what is going to be the equivalent of a syndrome function. So, let me consider all possible errors of this form. So, on each qubit, I will apply either the identity or an X or a Z. And actually, I'll go just a little further and add X and Z simultaneously. I'll possibly add a Y, which I'll define as X, as I times X, Z. Why this technicality will be apparent in a moment. So this is on what I'm allowing myself to do on one qubit, and I'm tensing this to the power of 5 to get a bunch of operators on 5 qubits. So these are the errors that I want to deal with. Let me define what I will think of the syndrome of an error, E. So what is this? It will be, like in the classical case, a 4-tuple of bits, S1, S2, S3, S4. So this belongs to 0, 1 to the 4. And how is SI defined? SI is going to be equal to 0 if E and MI commute, and 1 if they anti-commute. Okay. Why not? Now, I can define this function with a set of error operators. And now I want to define the set of states. So for S in 0, 1 to the 4, let me define CS to be those are states phi such that for any I equals to 1, 2, 3, or 4, mi times phi equals -1 to the power si, I hope this is readable, times phi. I'm allowed to define the set of states, and we remark okay, two things. C0 okay, contains a quantum code C, so our set of spaces, okay, the subspace generated by psi 0 and psi 1. Maybe this is not completely obvious, but more generally, we have this proposition. For E, the narrow operator, so one of those, and psi encoded state, like this, then what happens to E times psi? Well, it belongs to the subspace CS for S equal to syndrome of the error E. Continue on the last blackboard, so should be just a couple of minutes. Damn it. Yes, and maybe I can keep this. No. So why do we have this? Proof is very simple. Apply mi to E times psi. Well, by definition of Si, this is -1 to the Si times E times mi applied to psi. But now mi stabilizes psi, so this is nothing but -1 Si E times psi. So applying M1 has, depending on the syndrome value, just put a -1 in front of our state. That's it. And now the magic is this. Right, 1 minute. The magic is this. Our total Hilbert space, it decomposes into some of the C times S. And it's actually an orthogonal direct sum for all possible values of the syndrome. Why? Because if you look at the definition, it's all up there, of C of S, what is it? It's a bunch, it's states that satisfy a bunch of equations of the form some things times phi equals phi multiplies either by +1 or -1. So these are eigenstates of the operators mi. And now the mi, they've been defined this is why there's a little I in front of x times z. They've been defined such that mi squared is always identity. So its eigenvalues are plus or minus 1. And now, why is it important that our mi commute? Because they commute, there are operators that get diagonized in the same orthogonal basis. So if we take all the intersections of these eigenspaces, we get a decomposition of our Hilbert space into a direct sum of orthogonal spaces. This was a bit fast, but if you focus on the argument, you will be convinced of this. So we can measure the syndrome. This is the extraordinary thing that is happening. We can actually measure the syndrome of E. So we do this measurement, we know what is the syndrome of the error, and we're back to the classical problem, which is very much of the same form that we had in the quantum setting. In the case of the 5-qubit code, there is exactly a one-to-one correspondence. Maybe I will go back to this at the start of next lecture to give slightly more detail. There's a one-to-one correspondence between the syndrome values, the 16 syndrome values, and the 16 possible elements, so 4 to the 4, in the set of error operators E, if we want on every qubit only one error, only one operator of the form x, z, or y. There's something of a miracle, so every syndrome value to it corresponds one error of weight 1, just like in the example of the Hamming code that we had before. So it really is time for me to stop, because I've noticed that they were very strict on
Thank you, Gilles.
times.